No, it's just better to accept failure than
You like lectured about that in class. I'm not paying attention. I was working on something else.
questions about the homework tonight. Had somebody mentioned to me that they didn't, when I referred to M, I didn't explain it. M is the mutual inductance, L is the self-inductance of the coil. everybody a rotated Smith chart. I don't know if y'all got that, but I tried to send it by email, so I make sure everybody's got that. Those are very useful. So if everybody's ready to take the quiz, but let me just take care of a few things before we get the quiz. I wanted to do at least one of those problems for the assigned ones. You got a preference? And again, here's what this amounts to. These are choke coils, and in general, it's nothing more than the transformer that we make. Each one of these has a self-inductance L, and they'll be the same, and there's a mutual inductance M. Now, the general equation for the voltage across any one of these lengths will be V1, V2, they'll be symmetric, will be V1 is equal to J omega L I1. I didn't put this down yet. This would be I1, and this would be I2, plus J omega M, that's the mutual inductance times I2. And likewise, V2 would be equal to J omega, then M comes here, times I1, plus J omega L times I2. The reason you do that is you can make a symmetric, you can make a statement, this is equal to simply J omega, and then it's going to be simply L, and it'll be a matrix, 2 by 2 times really a vector I. You know what I'm talking about here? This is a matrix form where you have a square right there, then you have J omega out in front like this, but that's the reason the M goes here, not here. All right, you want I1, then I2, I1, I2. Okay, now, for the first, which problem you want? If anybody wants a special problem, then I'll do it.
The first one is an ideal common mode choke is shown below. When terminals, okay, so it's a common mode choke with lowercase a and b on the left side.
All right, hold on. This is A and B, and this is large A, large B. L, L.
When terminals uppercase A and uppercase B are connected.
All right.
The impedance measured across the lowercase terminals
Right.
is J 300,000 ohms.
300,000?
Yes. F equals 50 megahertz.
Go ahead.
When big A and little b are connected together, the impedance measured across little a and big B is 1 mega ohm.
So then they connect them like this and measure. And measure the impedance here, Z. Like y'all with me? The only reason he did it that way is so one is common mode, one is differential mode. Right? So here's the easy way to think about this. Remember last time I came down and I said, effectively, if it's in differential mode, and you see how if current's flowing here, the same exact current's flowing there, but in the opposite direction, right? So this is the differential mode right here. Well, in differential mode, the actual value of these two elements, effective value is just L minus M. Y'all follow me on that, class? For differential mode? This would be L minus M. That means the net impedance here, the Zn here, would be equal to J 300,000 would be equal to J times omega, which is 2 pi, times F, which is 50, times 10 to the 6. And then it's going to be, now think about this, we've got two of these, so it's going to be 2 times L minus M. Everybody get square on that, class? That's the first one. We'll talk about that in a second. For this one, you have the current, if it flows this way, it comes down here and it flows this way. These are the dotted terminals. This is common mode. All right, so for common mode, that means that the effective element values here become L plus M, L plus M. Everybody with me on that, class? Now the mutual, it's going to try to stop this because the mutual is going to be additive to the actual value of the self-inductance. So for common mode, what does he give you for the value? J,
1 mega.
so it's really 10 to the 6 ohms, and that would be equal to J omega, which is 2 pi times 50 times 10 to the 6. Then it's gonna be times 2 times L plus M. Everybody follow the logic of this, with me, guys? All right, so over here, I'm gonna start back over here. What I'm gonna do is first get rid of the J. I always do that. Then after that, I'm gonna try to minimize the amount of calculations I do. I've got 300,000, that's really 3 times 10 to the 5th. And I have 10 to the 6th there, so if I divide everything by 10 to the 5th, I'll get 3 there and I'll get just 10 there. And then I'm just gonna, I mean, at this point, it really can do what you want, but I need to find L, really L as a, or M. I need to get it separately. So at this point, let's see here. If you take this number and divide it into 3, what do you get? I need a single number on that side. It's 3 over 2 pi times 50 times 10 times 2, so it's, I don't care how you do it, I just need a single number over here equal to L minus M.
0.000477.
All right, now, I'll go ahead and say L is equal to 0.007 plus M. Okay, it's 2 unknowns. Over here, I've got 10 to the 6 and J's on both sides, so get rid of that, get rid of this, put a 1 here. Now I have that, right? So I want 1 over 4 pi times 50, right? Would be equal to L plus M. Yeah.
For the common mode, how did you get J times 10 to the 6th?
It's stated in the problem. If you look at the impedance. That was the impedance between small a right here and large B here. What do you get for that?
0.00159.
0.00159?
Yes.
Okay, so if this is right, that means my L or my M value here, or L, doesn't matter which one we get. We solve for L there, so we'll solve for M over here. It's gonna be equal to 0.0159. Minus L, and since that's L right there, that's 0.00159 minus L, which is M plus 0.00477. And you can see, that middle term, the only thing I have to do is say M is equal to, well, that's going to come to this side, so it's going to be 2M is equal to this. And if you can tell me what that is, I appreciate it. So you're going to have this divided by 2. Let me just put that down. This divided by 2 would be equal to M. I don't know what it is, but
It's 557 microamps.
557 microhenries. And if you take that value for M over here and plug it in here, what do you get for L? Y'all follow how I'm doing this? Just setting up 2 equations, 2 unknowns, solve for one in terms of the other, and go. What do you get?
1.035 milliamps.
Milli? Is that the answer? that's the process. Anytime you have it for common mode or differential mode, just identify the mode and replace the elements. If it's common mode, replace it with L plus M on both sides. If it's differential, L minus M, and that's it. Typically though, I don't know if this is actually based on a real choke. Typically, M and L are so close that the common, or the differential mode is just about zero impedance, right? Here, he's got a fair value, and the common mode is where the impedance is. That's where you'll get a mega ohm, 2 mega ohms blocking common mode currents. Okay, so that's it in a nutshell. Now, before I get into chapter 5, or chapter 10, any questions at all about the other stuff we did with the EMC, with where you got basically you flat out the first break frequency, which is 1 over pi times tau, right? And then you hit the second break frequency, this is 1 over pi times tau rise. And you're going down by 20 dB, then 40 dB, right? I showed you. That's how those problems work. Did you all follow me? No questions about that? All right, so now we get into last chapter, 10. And this is microwave.
I can start, one quick question. So like, just to confirm, when it says like the nth harmonic, that's like n times 10 to the 5th, right?
Well, it depends on what the fundamental frequency is. See, they'll give you a clock frequency, 10 gigahertz, whatever, 10 megahertz. That frequency is the fundamental clock. That's the cycling frequency. Harmonic.
Oh, gotcha, okay.
The nth harmonic would be n, whatever n is, times that.
Okay, gotcha.
All right, so now we get into microwave. I didn't bring down any Droid board, but when you think of microwave engineering, you think of either waveguides, I mean regular metal waveguides, or you think of things that are called low-loss Droid board. And let me explain this. When you have a lot of microelectronic components, say you got ASIC chips, all this stuff, and you want to mount them on something and have them communicate with each other when you're at RF frequencies, then, I mean high frequencies, then small distances are still order of wavelengths. Y'all follow me on this? So now you have to have things where you mount them in a way where you can get the characteristic impedance of any kind of waveguide you use to match the actual impedances, input and output impedances of the device, or else you get standing waves and get a real problem. You don't, the circuit will not work properly. So one of the things that they do when they create these, you might say circuit boards, where you can mount components and then still have communication rails, I call it that. They use something called Droid board. It's really a high frequency laminate. We'll just say Droid board. Now, Droid board is basically this. It's a top has a piece of copper on it. Then it's got some sort of dielectric, and the bottom is all copper. Epsilon relative here is probably of the order of 2.2 to 4 in terms of its value. That's not really high, but here's the thing about it. This gap right here is very small. All right, so this distance between their H is small. The thickness of the copper really is inconsequential. It doesn't matter that much. And this will be copper here, and this will be copper. Now, it's a very wide board in a very small distance between those two. It looks like a capacitor, to be frank about it. It isn't a capacitor. But here's what they do. They take this, and if you think about looking down from the top of this board, what they're going to do, they'll mount components here and here, and they might have a component here, and then they'll have an antenna here, something like this, and they have to communicate. So what they do is put a photoresist on this thing, and I'll just, you don't have to write this down, just listen. Try to get a different color marker. Remember, I'm going to look down, this is a square board, they'll put a photoresist on here. Y'all know what a photoresist is? Basically, if you know anything about photography, you know something about this. They're going to put down something that is basically a liquid, and then the liquid will harden. okay? Now, what they'll do is they'll use lithography, which means they have either X-rays or some high-frequency light, and they'll basically develop the resist that they want to come off, right? In other words, they'll expose it to this light, and it's called patterning. Then, when they develop the resist, after that, they'll pattern this. It'll be left like this, maybe. I'm doing this. There'll be one straight line there, just for example. Then they'll take this and put it in a solution, an acid solution that will get rid of all this copper. These things will not affect the actual dielectric down here, so they get rid of all this copper. And now they have one copper line right here above them. That copper line between here and this copper plane, ground plane here, will make up a transmission line, all right? And what it does is it confines the signal primarily between the top and bottom rails. There won't be a lot of signal. There'll be some, but it's a small amount of signal outside there because of the distance, the relative distance. Now, these rails, I call them rails, they're just like, they're conducting lines that go from one component to another. But if you think about it, this is very high frequency engineering. It's a transmission line that is, it's not a waveguide, it's a transmission line, so it works in the TEM mode, and it will allow communications between the devices. And the key feature of this thing is that when you have this transmission line, I'll just draw this here. When you have the Duroid board, you got one piece of copper. Actually, you're gonna have a whole lot of lines like this. And then here's the board. Now, between here and this ground plane here, which is copper, you have a characteristic impedance, and it'll be like a characteristic impedance that you measured it here of Z0 that you can calculate. There's an effective dielectric constant to this. There's an epsilon relative effective. And you can design this thing based on the width of the line. You can get any impedance you want. Now, Dr. Whitmer's book has some approximate formulas for both the effective dielectric and characteristic impedance. I'm really not interested in that. I'll tell you why. Because nowadays, they have, it's like, I'm not interested in showing you how to use a slide rule to figure out square roots or logarithms, right? You got a calculator, it doesn't harm. Nowadays, if you want a certain characteristic impedance when you've got a certain set of Duroid board, you basically punch it into a standard type of lithography system. It'll pattern the thing exactly the way you want. You want a certain characteristic impedance, it'll do it for any Duroid board of any thickness. And it'll basically lay out the lines of how they should go to minimize the distance. And actually the EMC, it's called crosstalk. So I'll tell you in his book, has anybody worked with this stuff? Anybody worked with high frequency lines? Duroid board? Have you worked with FR4 board? The green stuff, black green stuff? The mount? You have?
Like conservative?
Yeah.
Yeah.
All right. It is a printed circuit. This is a printed circuit board, but that's high loss. So that's for lower frequency stuff. This is not microwave engineering. All right, so in his book in chapter 10, if you've got your books, I'll just tell you what I was trying to expose you to. If you look on page 543, you'll see a microstrip. That's what I was trying to show you. It's termed a microstrip. And then if you look on page 544 and 545, he goes through in 545 to give you the characteristic impedance for a given width to height, and a maximum frequency, which is the equation 10.7. All these things, I want to just say this. The characteristic impedance he has there, it's based on data fitting. They measure a whole bunch. First, they'll do simulations with something like HFSS that actually solves the Maxwell's equation for all the frequencies, and they'll allow the width of those lines to increase, the value of epsilon relative to increase, and they'll get what's called a family of curves for the impedance, characteristic impedance. And then they find a formula that best fits it. It's something easy to use. So His equations 10.5 and 10.6 are the best fits to that. You don't have to memorize that, and I won't test you on it. I'm just telling you, those are best fits. But in the real world, you just put in what the characteristic impedances you want, and poof, it'll automatically lay the thing out for you. You don't need to worry about these equations. They're nice at least to be exposed to, but that's it. The key one is then 10.7. It's the highest frequency that you can actually operate in a TEM mode. Now, just put down TEM max or something like that next to 10.7. And in his book, he'll say F max equals, and he'll do it in terms of C over 4H times square root of epsilon relative. Now, H is the actual thickness of this laminate. Laminate is essentially the toroid board. We call it high frequency laminate because it is made by laminating copper. Tell you one other thing too. The thickness or the thickness of these copper lines, it's kind of an odd way to do it. They don't tell you the thickness in terms of mils or anything like that, or millimeters. What they do is they give you how many ounces of copper are used for 1 square foot. It's an odd way of doing it, but they'll say so many ounce copper. It translates directly into a thickness. All right, so in case you see that, what are they talking about? Just look it up on Google, and for they'll have 1/4 ounce, 1/8 ounce copper. It always baffled me why they did that, but I didn't do any of this. They did it, and I think it had to do with the fact that the manufacturers worry about copper because it costs so much. That's the only thing I can think of. Okay, now here's what happens. If you go beyond this frequency, and Whitworth doesn't prove this, it just says, then all of a sudden, you will get something that no longer is a TEM mode. You'll get a waveguide mode, where actually you're going to be able to bounce signals top to bottom, and then all bets are off. That's where the thing will just break down. So that's the highest frequency. By the way, that's a very high frequency usually. You're talking about 40 gigahertz. If you actually do the math on that one, for a typical thickness toroid. All right, now, I wanted to get that out of the way. I'm not going to test you on those calculations. Those are just stated. They're not proved. They aren't derived from Maxwell's equations. What I am going to talk about now is the lump element. This is in section 10.2. And this is where those rotated Smith charts come in. So I got a question. I didn't get a chance to do this today. Is it going to rain today or not? No? I only asked because I hope I have an umbrella. I don't think I
It says 30% around 12.
30%?
Yeah.
Is AccuWeather or weather.com?
Weatherbug.
Weather. I gotta say this. So, I'm not an aficionado of all these weather apps. There's Weather Underground, there's WeatherBug, AccuWeather, weather.com, and a few others out there. There's the National Weather Service, NOAA's stuff. And I looked at the forecast yesterday from these different ones. I've never seen more disagreement in my life. 80% chance of rain at 7 o'clock, I think it was, or 8 o'clock on weather.com. Basically no percent chance from AccuWeather. Then the other ones, look, this is forecasting. Who's doing this? How can you be that far off or disagree? They are. Anyway, I'm so glad that these people don't work in our industry. We have to make things that work statistically well. All right, so here we go. Here's the game in a nutshell. I have an impedance right here, some ZL, a load impedance, all right? Now, I have a transmission line. It could be a waveguide, but think of it. I have a transmission line of characteristic Z0. And what I want to do is have no mismatch of impedance. I want to basically impedance match this device. The way you did this back in the day when you had Smith charts, first exposure to them, what you did is something called either shunt or series stub tubing. You basically put in a shunt here usually, a short circuit shunt with L, characteristic impedance Z0. And you select the points, the distance from the load, L, call it L1, and the length of the stub, L stub. And you did it that way. Do y'all remember doing that? We'll go through one of those in a second. This is a parallel or shunt stub. Well, you don't want to do that with Duroid board. As a matter of fact, you don't want to do that with a lot of things because it takes too much, really, they call it surface area, or it's got a big footprint. These things can be long relative to dimensions that you're working with. Y'all follow me? So they're good for some things, but for a lot of things, especially when you're doing Duroid board and stuff like this, these things take up a lot of space on that thing, on the actual surface of that Duroid board. You don't want to do that. So what they do a lot of times is, here's the actual characteristic impedance Z0. Here's my load impedance ZL. And what I'm going to do is I'm going to put an element either in series first, some series element, I'll just call that some JX. And then I'm going to put an element in shunt here. This could be this, and this would be a J, I guess, what we're supposed to use is B, but it's really going to be an admittance. And I'm going to select these two components to do the same thing as these do. All right, y'all follow me? So I'm going to either have a series component first and then a shunt one, or I'm going to have a shunt component and then a series. You're going to see how this works. But first, let me review Smith charts and this kind of stuff. So I'm going to draw a Smith chart. And just, you don't have to write this down, just bear with me. It's been a while since you've done this, but I think I can refresh your memory. When you have a Smith chart, you basically have a big circle. And you have, I call it an equator right here. And you have a center point. That value is going to have the circles 1 up. Then you have these concentric circles that represent the normalized value of the impedance, the real part of the impedance. That's just for 1. This would be circle mark 1. And you also have trajectories, come this way, that are J something. J1 is the North Pole, minus J1 is the South. And then, the rest of the deal, you basically have larger and larger circles. The bigger the circle, the smaller the real value. This is going to be like a 1/2 is the real part for this. And this further out you go, this would be like minus J or plus J 1/2. But you get the idea. Y'all with me on this? Everything below the equator is negative J. Everything above the equator is positive J. And the circles, the real circles, are just concentric like this. This point is infinity. This point is 0 in terms of the value of the normalized impedance, right? And we also talked about something called, when you read these, it's wavelengths towards generator or wavelengths towards load. I almost always use wavelengths towards generator, just for reference. So when you look at this, and we do a standard problem with Smith charts. Let's say I want to do a shunt stub tubing, so I want to do this guy right here. And I want to figure out the values. So I'm going to make a problem. So I'm going to say I've got an impedance here, characteristic impedance of 50 ohms, and then I have a load impedance here, say, 25 plus J25. Here's my load impedance. And I would impedance match that. So first thing I have to do is what? You gotta normalize the impedance, right? You gotta take the load impedance divided by the characteristic impedance. So first thing I get this normalized impedance. That's simply ZL by Z0. In my case, I made it so it'd be 1/2 plus J1/2, right? Everybody remember doing this? Now, we're coming and we have to find that point. Approximately, where is it? Well, if you look here for a second, you can see that your entry point 1/2 plus J1/2, I literally made happen right there. I'm saying this is an approximation. This is the normalized ZL, right? Y'all remember doing this class? All right, now that's where you come in at. Then typically you're told to take a straight edge and draw a line right through the center here, and take your compass, and if you measure from here to here, you're going to transcribe a circle or like this. Y'all remember doing that? How many do? All right. This is a standard. This is very standard in electrical engineering. Smith charts, they're used a lot for a whole lot of high frequency applications. To this day, they're used. All right. Now over here, if I come down and I go to the conjugate point of this circle that I just, of radius, it's really the magnitude of the reflection coefficient. Here, now I get YL. You remember that? YL is simply 1 over ZL. So I'm gonna put that down. YL is 1 over ZL, correct? And I don't know exactly where that's gonna be, but let me, can somebody just do this for me? Can you take 1/2 plus J1/2 and take 1 over that? I have an odd feeling that might have a real value of 1. I hope I'm wrong.
It's 1 last J.
Well, unfortunately, that one, I wish I didn't. So what happens is, this is exactly 1 minus J1
Yes.
minus J1. Oh, God. So this isn't the one. So when I'm hitting right there, my real part is 1, right? So I don't need, I've already hit, I mean, remember, what you want to do with a shunt stub is you want to move till the real part's 1. It's 1 right there. I don't have to move. So if I go right at the load, and I just put a stub that would have an admittance of plus J1, y'all follow me? Then the thing's impedance max. So for this particular one, I don't need any distance here. This distance is effectively L equals 0. I can put it right here, but I need a shunt stub. And I need a shunt stub that will have an impedance. Remember, if you're dealing with, not impedance, an admittance, when you're dealing with admittances, you add them, if they're in parallel, like resistors in series. Do y'all remember this class? So I have to get rid of this minus J1. Now y'all follow me? That means I'm gonna have the the admittance of this stub looking this way. The actual normalized admittance has to be plus J1. Does everybody follow me on this? That way, if you add that to minus J1, you get 0. YL is equal to 1. 1 over 1 is 1, so the normalized impedance at that point would be 1. Multiply that by Z0, it is Z0. And you have a characteristic impedance equal to the impedance you're going to see with that stub added, so the deflection coefficient is 0. That's the basis for Smith chart usage, to get a reflection coefficient of 0. That's how you do stub. And this is a shunt stub. So how do I get YL equal 1? You remember this? I like talking about it this way. If you think about a stub, and I'm using a short circuit stub, what is the impedance of that load right there? If it's a short? 0, right? Y'all with me? If you got a short circuit, if 0 is the impedance, y'all follow me? 0 ohms, correct? Now, that is the impedance, but we're in the admittance domain, so the admittance of that would be 1 over 0 or infinity. Y'all follow me, class? So now the point you start at, and by the way, with a short circuit stub, it is just going to be, it's going to be exactly infinity. So you start right here on the rim. You're on the rim, right here. And now I have to move. I'm going wavelengths towards generator. I'm moving away from the load. I'm moving that way. And I have to move until I have an impedance of J plus 1. Now keep watching this. So I have to move all the way around to this point right here. Y'all follow me? That's exactly 3/4 of that circle. 1 full revolution on a Smith chart is half wavelength. Y'all remember that? So 3/4 would be 3/4 times 1/2, right? Or 3/8 of a wavelength. Y'all follow me? That means this load would have to be 3/8 lambda long, and that means it would attach your, if it was gonna be a short circuit stub, and you would have no standoff distance, you just put it right next to there, because it just happened to be, the values I chose landed right on that circle. Otherwise, you'd have to move somewhat away from the load. How many remember doing that? Some people reluctantly, no, I'm gonna admit that. Come on, guys, I mean, how many had Whitworth? How many had Riggs? How many had Bashir? Had El Bashir? He does that. I know he did this, right? All right, so anyway, that's the deal with Smith charts. That's how you were exposed to it. Now I'm gonna show you how we do them with rotated Smith charts to get these element values, okay? Because I just wanted to do this to kind of refresh your mind about this stuff. Smith charts, you use them at EMAG too, but you're like an EMC, we use them, all the high frequency circuit design stuff they do it with. I don't think they used it in analog electronics. Did you guys use that? But you're gonna use it for a lot of courses in real electronic design, high frequency electronic design. And you have to be familiar with this. In industry, to this day, when you get spectrum analyzers and stuff like this, or network analyzers, and you look at actually analyzing the circuit, that pops up. And one other thing that we're gonna get into, S parameters pop up. You use them all the time. So now, we talk about the rotated Smith chart and how we do it. Remember the problem, I've got a characteristic impedance Z0, and I have a load out here, ZL. And I want to find elements now, not lengths of line that are shorted or open, elements that I'm going to stick in there and do the impedance matching. Follow me? So to do this, I need this rotated Smith chart that I'm going to try to draw here. And it's just a basic Smith chart, except it has two circles. Now it's going to have the R=1 circle that goes right through the center. And it's also going to have the conjugate circle. Same exact size, both of them go through the center, but this is the conjugate circle. All right? Just take this and roll it over here and put it up there. All right? Mirror it right down the vertical axis that separates the halves, and you'll get that. And I might as well do this. I'm going to put the J1 here, and J-1 here, minus J, actually. And this is infinite, this is 0. And now we go through how we go about this. So there are really three things you have to worry about. If the actual value of ZL over Z0, this value, which is the normalized impedance ZL, if it's inside the one circle, now here's what I mean by that. Let's just take an example. Say ZL over Z0 is 2 plus J2, okay? So if you think about this, here's the one circle. The real part 2 is about here, right? About. And J2 would be about here, so it would be right about here. This would be ZL. Y'all follow me on this class? Now, hear me on this one, just listen. We know the goal of all these impedance matchings, any way we do it, we want to be able to add or subtract something that will not cause any resistive losses to this, so that we can get to the R=1 circle. Because as soon as we're on the R=1 circle, the imaginary part of it we can get rid of by adding either a series or shunt element. You all follow me? And then we'll be right here. That's where our goal is, to get there. Well, on this one, now just think about this. This is the 2 circle. Well, I should put it right here. This is 2 plus J2, right here. I'm trying to just show you this. No matter what imaginary value I add in series with this, it will only change the position on this R=2 circle. The R=2 would never change. Do you all see that? So I can never get to the end by adding a series element. So if you're inside the one circle, you go to the admittance domain. So then you say YL is equal to 1 over ZL is equal to 1 over 2 plus J2. Now, can you give that to me? This one isn't going to be 1. That I guarantee. And if you can do it, I appreciate it. I think it's 0.25 plus J, or minus J.25, but I don't know.
Yeah, it's quarter minus a quarter J.
All right, so this is 1/4 minus J1/4. All right. Now that right there will be at the conjugate, if I was right through the center, right? And had this line with that line, I would be at YL, right? Just think about this. With me, everybody? I want to get to Y. Y is 1 over Z, so it's the conjugate point of the circle you would draw here. Y'all follow me on this, class? How many understand this right here? Right? Okay. Now, once I'm there, hear me. I would like to move to the rim either this way or this way. Now remember, these are going to be moving along the J. You're going to have a constant real part of 1/4, but you're adding or subtracting values of J something, which is going to be an admittance, something in parallel, until you get here or here. And the reason you want to get here or here is because now, remember, that's an admittance, but then if I take that and I look at it as the impedance, it's actually on the one circle. Do y'all follow me? And then I can add an impedance element and get rid of that J component. Y'all follow me on this, class? So just bear with me. So here I come down and I have a value that's 1/4 minus J1/4. And I want to add something to it to get to the rim here. Now in your book, Whitmore's got an example of this. Well, let me go ahead and say this. Does anybody have the rotated Smith chart here? You got it? We're gonna do something. Can you get that point? Conjugate point right here, good, 1/4 minus J1/4. See here. This is gonna be 2.24. Yeah, right there, you gotta extrapolate, go down this line, and you gotta get to this quarter circle, so that would be 0.25 would be about there. Keep going down here.
I'm just gonna do it on here.
Yeah, go.
Nice.
Yeah.
I never do that.
Follow that
Like I could never mess with
onto
it.
this one. You all follow? See where I go? And you see
I just
how
drew
you-
oblong circles somehow.
Oh.
And look at
Yeah.
0.4.
Oh, circles are so hard to draw on this thing, because it
Yes.
always goes like 2
Yes.
It's weird.
Your circles are complex function.
Yeah, I want this value right here.
Please add
Pardon me?
this. That'd be great.
All right, so this is J 0.44, you said?
Yes.
And it's got a real value there of 1/4, right? Alright, so, hear me on this, just listen. I had a value of minus J1/4, I move, I'm gonna add a J to it until I get here. So what I need to do is find out the value of J.044 and add 0.25 to it. Can you give that to me? So, I have to get 0.44 and 0.25, that's 9. So it's, I have to add 0.69J this is gonna be in parallel. It's gotta be a shunt. Do y'all follow me? Because we're in the admittance zone. So that means over here, the first element I'm gonna get is gonna be in shunt, and it's gonna have a normalized admittance value of J 0.69. So this is gonna be J 0.69. All right. So I started over here, I'm inside the one circle. If I'm inside the one circle, I've got to go to the admittance domain. That means I'm adding things in parallel. And then, when I'm in the admittance domain, the value I'm gonna add, I got by going to this point. You all follow me, class? Yeah.
The admittance domain is the left circle.
Well, it's always gonna be, it's not necessarily the left circle. Where, if you come in with impedance, take 1 over impedance.
Oh, right.
You're in admittance. So, when you're in admittance domain, we're gonna get to the rim of either here or here. So I added a value of J 0.69. Now, I'm right here. Now, would you do me a favor if you have a calculator and take 1 over, I'll tell you where I'm gonna hit. I'm gonna hit somewhere on the rim here, where, and the real value will be 1. Because this point and this point are exactly the same distance from the center there. So take 1 over 1/4 plus J 0.44. You're gonna get something real close to 1, it'll be like 0.99, 0.9987, something like that. Anyone?
So 0.44.
What?
Yeah, 0.976 minus 1.7 J.
All right, you get, anybody confirm that?
I can confirm that.
0.9, so this point, it should be 1, but it's 0.976 minus J what?
1.72.
1.72. This is about 1, all right? And I'm eyeballing that, so it's not as sharp, but it'll get to be 0.99 something usually over here for the real one. That's what you want, right? Now I've got to get rid of this part, right? That's a minus J 1.72. I need to add a plus J 1. Now I'm in the impedance domain, right? I was in admittance. Now I'm in the impedance domain. I got to get rid of that, so I add a plus J 1.72. So here, I just have J 1.72, and now when I do that, after that's done, then I have a real part of 1 plus J 0. That means I'm right here, smack dab in the center where I want to be, because that means I'm impedance matched. Do y'all follow me, class? That's the goal with this. Now that's, again, for the condition that the normalized impedance is inside the one circle. I've got to go to the admittance domain. I've got to add admittance till I get to the rim of the rotated circle. And then from there, I go back to the impedance domain and I land on the rim 1 plus J something or 1 minus J something. And then I get rid of the J by adding an impedance. Now, next thing is, so what does this J 0.69 represent in terms of an element? Follow me? All right. So if we are talking about a positive J or negative J, what I like to do is think about elements in both domains. So if I have an inductor, L, all right, if I'm in the impedance domain, all right, the impedance of an inductor is J omega L. All right, if I'm in the admittance domain, the admittance of an inductor is 1 over J omega L, or it's minus J over omega L. That would be for an inductor. If I have a capacitor, the impedance of the capacitor is minus J or 1 over J omega C. The admittance of a capacitor is simply J omega C, right? I'm just showing you, I'm trying to make sure everybody's got their head on straight on this. Right? I didn't normalize anything, I just showed you. Now, if you come here, and now you talk about the normalized impedance, that's J omega L over Z naught. If you take a look at the normalized admittance, it's minus J over omega C Z naught. By normalization, it means you're dividing by the value of impedance, so it is relative or scaled according to the impedance of characteristic impedance. That's normalization. If I normalize the admittance over here, then I take this and I flip it, so now it's multiplying by the impedance. And this would be Y normalized. Everybody everybody with me on how I'm getting that, right? I want to deal with normalized values, because that's the value I got here. So, take a look, and let it sink in, and just answer this question. So if I want to add in the admittance domain, J.69, what element am I going to use? Look in the admittance domain. What value has a positive J? Is it capacitor or inductor?
Capacitor.
You all see it? It's the capacitor in the admittance domain. It's this. So that means to get that value of capacitance, I put J omega C Z naught equal to J.69. We're going to get the value of the capacitor here. It's going to go there. So we have J 0.69 equal to J omega C times Z naught. You all follow me? I'm making sure you just see exactly what I'm doing. Now to get the value of C, it assumes you know the frequency and it assumes you know Z naught. That means the value of C will be 0.69 divided by omega and Z naught. And that's the value of the capacitor that will go right there. So I'm going to go ahead and put the capacitor there. That will be the value of this capacitor. Now, look here. That's a series element. That's a normalized impedance, right? If it's in series, it's impedance. If it's in parallel, it's an admittance. Do y'all follow me? J 1.72, what element is it going to be? Is it going to be a capacitor or inductor? Inductor, it's impedance, right? Now you come over here. Here's the normalized impedance of that inductor. Remember, these are normalized values. So we come over here and we're going to say J, find the inductance now. We're going to have J times omega times L over Z naught equal to J 1.72. Everybody with me? I just equated that. Put that value equal to the normalized impedance over there in the inductor. Nothing mysterious. Then after that, I'll get rid of the J, obviously, and I can say that L will be equal to 1.72 times Z naught over omega. So whatever Z naught is and whatever omega is, determine the value of C or L in this case. Are you all with me? I want to take you to the next step. And I'm going to just let it sink in. Any questions about this? You could almost guess is what's going to happen. Now, what happens if the normalized impedance is in a rotated circle? Well, you do the opposite. Then the first thing you do is add a series element, and then you'll add a shunt. Here, first thing we did is add a shunt element, then a series element. All right, so if it happens, and I'm going to go ahead and just erase this. But this will make sense to you. You have to keep up with it though, because if you don't, when you try to cram this stuff, it's real confusing. So now, here's the deal. Now I'm going to have ZL over Z naught, which is considered the normalized impedance. This is going to be inside the rotated one circle. So I need to redraw this. There's my one circle, there's my rotated one circle. Now let's pick a value inside the rotated one circle. Say it's 0.3 plus J 0.2. I think that's inside the rotated circle. So J 0.2 would be here, and 0.3 would be about here, I think. So this would be the point. This is ZL. And it's equal to, put it down here, I'm gonna assume ZL is equal to 0.3 plus J 0.2. Can you confirm that's inside the row? I'm almost guaranteeing it is. All right? Now this is an impedance. Now hear me. So that's an impedance. What I want to do is, if you think about this, these are going to be, here's the J lines there. So this is J.2. The real part of this impedance is 0.3. No matter what value of J I add to this, since if you look at this, let me back up for 1 second. I can add a value J, that's what I'm trying to say, to get to this rim right here. Y'all see this? Now remember, this is impedance, so this is 0.3 plus J 0.2. I want to add something to get to the rim, and the rim's going to have a real value of 0.3, and it's going to have an imaginary value of something else. Is there a possibility you could get me that value? Just go up the 0.3 line until you intersect the top part there.
0.46.
It's a value of J 0.46? Okay. So this is going to be 0.3 plus J 0.46. It means over here, it's J 0.46. I'll trust you on that, all right? Now, if you take that, so I'm going to add, now I figure out how much J I added. I had a J of 0.2, I ended up at J 0.46, so I have to add J 0.26. Do y'all follow me? This is 0.2. I need the imaginary part to be 0.46. So I have to add 2.26J. Y'all with me? So that's a series element. Now I have to add a series element of J 0.26. That's normalized. That would be an impedance. And now I'm on the rim here. Okay. And if we do this right, it's going to come out to be, now I go to the admittance domain. That's still impedance. Now I go to the admittance domain. I come here to the conjugate point, which is 1 over 0.3 plus J 0.46. Can you give that to me? Y'all follow me what I'm doing? I get to here, that's impedance. I want to go to admittance because I'm going to add something in parallel. What do you get?
I got 0.994 minus 1.5.
Or minus J what?
1.5.
1.5? Okay, so 1.5. All right. Now I'm in the admittance domain, and I have to add a plus J 1.5. Do y'all follow me? To get rid of that minus 1.5? And then I've got 1 left, and that's what I want. So now I'm going to come down here and have plus J 1.5 here. And it's going to be in shunt or parallel. Y'all with me? I want to make sure so how do I get, this is a series element, right? And it's got a plus J. What has a plus J? The L or the C, and if it's impedance. Just look like. What's the impedance of an inductor? Plus J omega L, right? Normalized would be plus J omega L over Z naught, right? That's what this is. So I would have J 0.26 equal to, and this would be J omega L over Z naught, or simply L itself would be 0.26 divided by omega, and it would be times Z naught. That would be the value of L that goes there. Can you follow me, class? What about this? That's an admittance normalized. What element is it? It's a capacitor, right? You all see that? So now I take J 1.5 here and equate it to, what's the admittance of the capacitor? It's J omega C, right, times Z naught normalized, correct, class? So now I can get the value of C, and it would be equal to 1.5 divided by omega, right, times Z naught. All right, finally, I wanted to cover this today. The last thing I'm gonna say is, what happens, you know, if you're outside both of these? Doesn't matter where. Well, in that case, it doesn't matter if you put a shunt or series element first, and here's why. If I'm outside either of these, okay, y'all realize that if you take a look at this, if I have, just look at this, I want to get to the one circle, so if I'm here, I can add plus or subtract plus J something and get here, right? So I could have a series element, then I'm here. And then I could go to the admittance domain and add a shunt element, all right, that would get rid of the imaginary part. Do you all follow me? It's the same technique. Or I could go to the conjugate domain, all right, and then I could move to the rim, either here or here of the admittance domain. And once I'm on the rim there, I go back to the impedance domain and find out what the imaginary part is of the impedance and get rid of it with the proper element. Do you all follow me? So I'm gonna give you a bunch of problems to do this weekend, and on Monday, we'll go through them. And bring your Smith charts, bring your protractor, bring a straight edge. You should bring a compass and a sharp pencil. Bring a bunch of Smith charts. Print them out and bring them in. So now for your quiz, I'm gonna ask you, you want it now or you want it on Monday? Because if you're ready for it, it's by Saturday. I only want it now. Okay, you ready to get it? You're gonna get all the time you want.